Good afternoon, everyone. Thank you for being here. I'm Yuan from Tencent Security Yunding Lab. And today, I will show you how we are enhancing static code analysis using large language models and customized data flow analysis. So first, I will introduce what SAST is. Next, how we can use LLMs to automatically identify source and sink functions. Then our customized enhancement to data flow analysis. And finally, the results demonstrating the effectiveness of our approach. What is SAST? SAST means Static Application Security Testing. Using SAST tools, we can analyze source code without running the application. For example, detecting SQL injection bugs. From the picture on the right, we can see that SAST is now an essential part of DevSecOps, automating security checks. Popular tools include CodeQL, Fortify, and so on. What is CodeQL? It's now a product under GitHub. Queries and libraries are open source under the MIT license, including DFA part. But the core engine is proprietary. The workflow of CodeQL has 4 steps. First, download the source code of the project. Then, create a database using CodeQL command. And then, write a QL query and run it against the database. And finally, the query results show whether there are any bugs. And on the wall of fame of CodeQL, we can see all the bugs uncovered by CodeQL. It's not a complete list, but so far it has found 418 bugs. And the number is still increasing. Also, on GitHub, we can set up our projects to run CodeQL scans, either on a schedule or whenever there's a pull request. So does it mean no bugs anymore? We tried using CodeQL to detect recent high-risk bugs, like the ones listed in this table. We found there were a lot of false negatives. We analyzed the root causes as listed in the last column and found 2 main reasons. First is incomplete source and sink coverage in built-in propagation rules. Second is disruptions in data flow due to insufficient support for certain language features. For the first problem, I will introduce how to use LLMs to recognize source and sink functions. We have noticed that current methods rely heavily on manual work. One approach is manual definition, where developers have to manually review the source code to identify sources and sinks. Another way is through community contributions, like CodeQL has default rules. From the picture, we can see that key information includes library, module, function name, but we have found both methods are pretty labor-intensive. So is there a way to automate this process? First problem is, where should we look for sources and sinks? We have found that source and sink functions are actually API functions from third-party frameworks. From the picture on the left, we can see that SSIF sink actually is an API in REST framework. And the implementation code for these API functions can be found in open source frameworks. So we can detect sources and sinks by scanning those frameworks. The second problem is how LLMs can help. On the right is the workflow of our method. It has 3 AI agents. We first use the Discover agent to identify potential source and sink functions in the framework. Next, the Judge agent applies expert rules to check the functions and remove results that don't align with expert experience. Finally, the Validation agent runs queries to verify that the functions are used in real-world projects. First, we run a coarse-grained detection at the file level, feeding the source code file and the prompt to the model. In the prompt, we mainly describe the characteristics of the functions we need to identify, which are related to the programming language and the bug types. For example, for SSIF bugs, the sink functions are typically those sending HTTP requests. And on top of that, we can set constraints on the format and style of the response. And you can try different prompts to get the best results. And this is just a reference. And for the LLM's result, we'll remove results with low confidence scores. And the threshold can be adjusted depending on the prompt and the model you use. And in the end, we'll get a list of source and sink functions. To remove the false positives from the previous step, we move on to function-level filtering. We check both the function names and the function code. For example, with SSIF, the sink is a function that sends an HTTP request, while for SQL injection, the sink is executing a SQL statement. And we have noticed that long-thinking models tend to perform better at this stage. And again, any functions that don't meet the criteria will be removed. In the end, we collect all the source and sink functions present in each framework. Besides having the LLM directly scan, we also need to integrate expert experience. The experience comes from the community's long-standing practice. For example, the function should be publicly accessible. The function should have return values that propagate tainted data. And the function should, the return value of the function should not be of the Boolean type. And there are plenty of these expert rules. And again, they can be added or revised based on different bug types or taint types. And we'll use the LLM to apply these expert rules to check the function name and function body here, and removing functions that don't match the expert rules. The final step is confirming that the source and the sink we have identified are actually used in real projects. First, we have to head to the framework project homepage and find the dependent page. And this page lists most of the open source projects using that framework. And next, download the source code of these projects, sorting them by star count from highest to lowest. And finally, run a SAST tool like CodeQL with the new source sink rules applied to scan these projects. And based on the scan results, verify if the newly added source and sink is actually used. And any source or sink that isn't used will be removed. And for the second problem, I will introduce our enhancements to DFA, data flow analysis. What is DFA in CodeQL and the other SAST tools? On the left is an example of data flow analysis in CodeQL. It works by extending data flow config.sig here, and implementing the isSource interface at line 10 and isSync interface at line 16, and then calling flow path to perform a global taint analysis at line 27 here. So on the right are the results. From the results, we can see a list of numbered path nodes, and this list represents a complete data flow path. And each path node has two parts, the node and the access path. So how does the whole process work? And this diagram shows the workflow of DFA. First, CodeQL provides the config.sig user interface, and you can call the flow path API, just the last previous slide. And then there are two key concepts, node and access path. Node is calculated through forward flow and reverse flow. Forward flow is the forward propagation from the source point, while reverse flow goes the other way, tracing backward from the sink point. And together, they form a complete source-to-sink path. And access path is calculated in 5 stages, from stage 1 to stage 5. Each stage adds further details to produce the final result. We use forward flow to illustrate how node is calculated. On the right is the diagram of CodeQL source code, which consists of different steps, such as jump, store, and details are in the table. First is the source step, which sets the starting point for data flow. Next, the local flow step, which handles intra-procedural analysis. And then the jump step, it provides the interface for custom propagation from one node to another. There are two interfaces, a user-level interface through its additional flow step, and a system-level interface through additional value step. And then comes the store and load step. Store is writing a tainted node into a field, array, collection, or map content, while load is reading a tainted node from them. And this is the core of access path. And finally, call in, call out, and call through steps, which deal with inter-procedural analysis. Call in handles propagation from actual arguments to formal parameters. Call out and call through deal with propagating the return values. And the difference is whether the return value is propagated from external sources or parameters. And notice that post-update nodes here represents nodes that are implicitly updated as a result of a function call. So what is access path? It consists of a content list and a type. Content is basically a way to describe how data can be stored inside an object, and details are in the table on the left here. So for a field type, its content is simply the field name. For other types, it's more of a generalized result as shown in the table here. And access path keeps track of the content propagation relationships for the 4 types of nodes: field, array, collection, and map, during store and load steps. And the table here shows examples of access path. So for example, in this row, the content is name with the type string. Then how to calculate the access path? So on the right here, we write a sample code. From the table, you can see how the intermediary value access path changes at each stage. At the beginning, in stage 1, there's no AP at all. And at stage 2, AP becomes a Boolean type, indicating whether a content operation exists. And at the last, we find that the complete access path is a content list here and a type. And after an overview of DFA, now we introduce about some of the challenges it faces, using Java as an example. So static analysis tools include CodeQL, face challenges such as cross-thread issues, reflection, and value parsing. So here's an example of cross-thread analysis. The parameters of the static main method are the source point, and the print line method parameters are the sync point. So on the left here is the code, and on the right is the intermediate results of the static analysis. And as we can see, in the default analysis, we can't find a path from source to sync. It breaks at the constructor call of runnable demo at line 14. So how do we connect it? Remember the jump step we previously introduced. We can use jump step to jump from the runnable demo call to the instance parameter of the run method, namely this parameter. And after the patch, we get the complete path. So to summarize, when the taint is propagated through the constructor of a runnable instance, our approach is to jump from the constructor call to the run method. And this is the implementation using the additional value step interface. And we complete the jump step here. But what if the taint isn't passed through the constructor, such as through assignment statement in a function call at line 8? How do we handle this? Our solution is that if the taint exists before the start interface is called, like line 17, we take the caller of the start method and jump to the instance parameter of the run method. So from here to here. So in this case, jump from the line 18 to 10. And after the patch, we can get the complete path. And what if the 10 comes after the start interface? In this case, line 23. Our approach is to find a node matches 3 conditions. First, this node is a post-update node. Second, this node is a runnable instance. Third, this node has a store operation. So we jump from that node to the instance parameter of the run method. So in this case, jump from line 8 to line 10. And after the patch, we can see the complete flow is detected. Next, we'll introduce the second challenge, Java reflection, and take the invoke method in this code as an example, which is line 13. We are facing 2 difficulties here. First, how do we pinpoint the method that invoke actually correspond to? So, namely, what is the method at line 13? Second, how do we fix the propagation relationships for interprocedural calls, like call in and call through? So from the red line, we can see that the parameter propagation logic is different from the normal call process. For challenge 1, there are 2 solutions. One approach is to track the method instance, as illustrated in this diagram. And the other is to determine the method based on the number and types of parameters in the invoke method. And we have implemented both methods. And note that this tracking requires global data flow analysis. The second challenge, how do we make reflection analysis work within CodeQL's data flow? We mentioned earlier that additional value step can define edges to connect to nodes. But here's the problem. You can't use data flow inside additional value step because doing so would cause a non-monotonic recursion issue. Basically, you need data flow interface in additional value step, but the data flow interface depends on additional value step, so as illustrated in the diagram. So how to fix this? We can create a copy of the data flow analysis implementation and have our reflection analysis rely on the copied version, as illustrated here. And then we patch the original data flow here to avoid any dependency issues. And to support the invoke method, we fix the parameter propagation logic for call in and call through. For example, for call in, argument propagates to parameter, and object propagates to the parameter this. And here's an example for reflection. Firstly, the data flow breaks at the invoke method at line 13 here. And by adding reflection analysis, as shown in steps 1 to 4, we can propagate from tend_s here to tend_object here. And thus, we get the complete path. And next, pass by value in Java. So first, what is pass by value? In programming languages, parameters are generally passed either by value or by reference. And in Java, the way actual parameters are passed to methods is passed by value, not passed by reference. So if the parameter is a primitive type, and what gets passed is a copy of the actual value of the primitive type, and a copy is created. And if it's a reference type, what gets passed is a copy of the address value in the heap of the object referenced by the actual parameter. And just like with primitives, a copy is created. So what's the problem? And on the right is a case where a copy is stored in a field. But the problem is there are many copies, like a person, P, and D.A here in this example. So the core issue is that when the value is modified in one copy, all its copies need to be updated. So in this case, it is the parameter person P in the constructor of demo field instance here. The copies are indicated with the blue line here. And here's our solution. So first, we have to locate the field, which is of a non-primitive type. And in this example, it corresponds to field A. For this field, find its store operations, identifying both non-post update node and a post update node. So in this example, it corresponds to line 7 and line 11. Line 7 is a non-post update node, while line 11 is a post update node. And for non-post update node, store operations use global data flow to locate the parameter and the actual argument. So in this example, and as shown in the red dotted line here, we located the parameter P here in the demo field constructor. And for another store operation of a post-update node, we add a mapping from this node to this node. So this is the jump step we have previously introduced. And we have to use global data flow because we might encounter scenarios like inter-procedural calls, store and load operations, and so on. And then I'll introduce the results of our research. We have found about 190 source and sink functions across 18 Go frameworks. We also scanned over 5,000 projects and found that the detected data flows increased by more than 15%. And we used this CVE we found to show how a new sink could lead to a detection. And this is a SQL injection bug in traffic ops, part of Apache traffic control project. This project has CodeQL enabled here, so which means it is false negative for CodeQL. And here's the data flow of the bug. First step is to read the parameters from user input here, which is a user's comment, and then process and validate the requested parameters as illustrated here and this info.go file. And finally, when inserting the user's comment into the database here, it calls the query row X function. But when we checked CodeQL's detection rules, we noticed that query row X function isn't included in the sink model. And we scanned the SQLX function framework and found this sink, as illustrated here, and thus we detected the bug. And with our enhancement, we can detect historical CVEs that were previously undetectable. And in this case, adding the source function enables the detection of 3 CVEs. Several open source projects are affected. And for this CVE, we fixed cross-thread and missing sync rule, and thus we can reproduce this CVE. And this CVE proves the effectiveness of our reflection enhancement. And we also found many new bugs, and here are some cases below. And finally are our takeaways. So first is that semantic analysis of code in SAST is particularly suitable for LLM-assisted analysis, and their combination is a research direction. Second is that CodeQL's data flow analysis mechanism is highly representative, serving as a good start for learning data flow analysis. And third, CodeQL's data flow analysis is not perfect and can be studied, modified, and improved. So, any questions? And also, please feel free to reach us through the emails here. OK, thank you.